We are talking about homology today, yes. So, actually this lecture, it takes me back to my youth. When I was like, I don't know, 3 or 4 years old, something like that, my mom taught us what a triangle was. And then wherever we went in the car, like me and my little brother Bill, we'd be like, Mommy, a triangle. We saw triangles everywhere. And so that's kind of what this lecture is about. All right, so triangulation. What's a triangulation? So that's more or less what we want to kind of explain. What is a triangulation of a space? Means what? All right, so to get to that concept of what a triangulation is, I need to kind of build up some theory. All right, so let me just get right to it. So this is all happening, we're going to do, everything's going to be happening in Rn, right? But these ideas could be, they can, everything I'm going to do is in Rn, but there is a way of doing this in abstract spaces. All right, so it's, but I'm going to stick with Rn. So here's the deal. Definition, and credit where credit's due. I'm in Manifolds, Tensors, and Forms, an introduction for mathematicians and physicists by Paul Rentland. I found that his few pages on simplicial homology is just really easy for students to understand and actually gets us to a concrete calculation of homology in not too much time. So, okay, so first of all, a set of points. So take a set of points, P0, P1, PD, in Rn is a finely independent. All right, a finely independent if P1 minus P naught, P2 minus P naught, PD minus P naught are linearly independent in the usual sense of vector spaces. So a set of points is said to be a finely independent if the difference between everything in the first point gives you a set of linearly independent vectors. This is a so-called a finely independent set of points. A simplex What's a simplex? A simplex is the convex hull of an independent set of points. All right? And he says we write, so let's call the set of points S, all right, again. And he says we write, all right, here goes, S, like this, S with brackets, to denote the convex hull. That denotes the simplex determined by the set S. And he says, so this is convex hull of S, all right. The convex hull is the largest convex set which contains the set of points S. So you could think of it as the intersection of all possible convex sets which contain those points. Smallest, not largest. Smallest, yeah. Sorry. Yeah, smallest, largest, same difference. Well, this is very exciting. Cool. All right, nothing relevant to class anyway. Okay, so just to demystify it, if S equals to, say, P0, P1, P2 as pictured, so here's my S, these 3 points, then the convex hull is the so this would be that. So all right, notation. Now, furthermore, if the cardinality of S is equal to D plus 1, then this is a D-simplex. So my example is a what simplex? Right, this is a 2 simplex. If I had, a P4 and a P5 down here, and I looked at, P4, P5 like this, that would be a 1 simplex. And it would just be as a point set, the line segment, 1 simplex. All right. So a triangle is a 2 simplex. A tetrahedron is a 3 simplex. All right. The vertices of a simplex are what? All right. And furthermore, because a subset of an independent set of points is itself independent, any proper subset of an independent set of points itself determines a subsimplex. All right. So if I'll still write it here, if T is a subset of S, right, then that determines a simplex T is also a simplex. All right. And if it's a simplex, if this is a K simplex, then it forms a so-called K face of S. Is the combination of all faces the boundary of S? Let's see here. So the set of vertices are 0 faces, right? Like each vertex considered on its lonesome is a 0 face, right? And like P0, P1 would be a 1 face of that 2 simplex up there. So yeah, I think that's fair. The set of faces of a simplex forms its boundary. But there could be some duplication there, right? I mean, like if you've already got the 1 simplex, if I'm looking at a D simplex, right? And I look at the D minus 1 faces, seems like that should get the edge, right? I shouldn't also need D minus 2 or D minus 3, right? Like if I look at the 1 simplex, one faces of this, I've already got the edge.
So it's only the faces of D minus 1 dimension.
Oh, in fact, those have a name. Sorry. Well, he says that n minus 1 faces are face sets. 1 faces are edges. zero faces or vertices. Fine. Okay, moving on. So we come to the definition of simplicial complex. What is a simple definition? A simplicial complex K, all right, is a finite collection of simplices which satisfy two properties. One, if S is a simplex in K and T is a subset of the vertices of S, then guess what? The simplex generated by T must also be in the simplicial complex. In other words, if it has a D simplex, it must have all the faces of the simplex also in the complex. And two, if you took any two simplices, if you will, in the simplicial complex, then if we look at S1 intersect with the simplex generated by S2, we get the simplex formed by the intersection of the vertices. What that says is that if two simplices meet, they do so along a mutual face. He says that the dimension of K is the maximum dimension of all the simplices which it contains. So the dimension of K is equal to the maximum, max D, such that, S is D simplex. I don't know how to say this. You know what I'm saying. I just don't have the words here. That make sense? It's like the largest, whatever that is, whatever the largest simplex is in the collection of simplices, that's the dimension of the simplicial complex. He says, intuitively, a simplicial complex is a set comprising a bunch of simplices that are glued together along their faces. All right? Now, not being content with what we've already done, we now add another wrinkle, oriented simplex. What's an oriented simplex? Right? Would be something like sigma bar, which is equal to L'Engle, P sub 0, P1, dot, 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 P, well, I could, fine, I'll stick with his notation, Pn. I mean, you could do, I could put the D from before. It doesn't have to do with, I actually kind of prefer D here, because I'm thinking of Rn at the moment as the universe in which this is happening. But I do think N is used differently in this section as we go on, so I should probably not be too married with that idea. Yep.
I'm not understanding why we make the distinction between a finite infinite and the infinite. Why is P not in that? You're explaining it to be intuitive differences.
Because we're trying to describe a triangle, not a plane. Like, I need three things.
Finite independent is referring to a set of points.
Right.
And then it's talking about vectors.
I would say that's fair. If finally independence is referring to a set of points, linear independence is really more about vectors. But that's kind of, that's baloney. I mean, because we can always make an interchange between vectors in points, but I guess those are vectors based at the origin, right? So in our usual thinking, p sub 0 is just set to 0 if you wanted to make the, yeah. Now an oriented simplex, we could have been saying oriented simplex all along, right? What's the difference? The difference is just that we put the things in S in order, all right? So there becomes a distinction between this and if I was to switch the order of the vertices. So this is the simplex with the vertices in this order, P0 to PD. All right? Oriented simplex. As a set of points, as a point set, this is also equal to this, all right? I mean, these are different objects, but if you just want to forget about the orientation for a second and just talk about the set of points, as a subset of Rn, these are equal. This is the simplex, possibly unoriented, with these as vertices. As a set of points, as a set of points, this is the same as that. But as a set of points, I could just as well do this. But I would not, as oriented simplices, say that this and that were the same. They're not the same as oriented simplices, but they are the same as a set of points in Rn. Forgetting about the orientation momentarily. Let me erase that. Okay, so he says all the simplices are divided into precisely two equivalence classes or orientations, depending on whether one chooses an even or odd permutation of the vertices P0 through Pn. So let's see here a couple of examples. Well, actually, let me save the examples for just a minute. Definition, because in order to make good on the examples, I need to really explain the examples about the right, I need to do not the next three definitions. Let's get to it. So, what's an oriented simplicial complex? Same as what I just wrote, except with orientations, right? But we also define, next definition, lots of definitions. An M chain, what's an M chain? An M chain on K with coefficients in R is a formal linear combination of the oriented M simplices in K with coefficients in R. In other words, is C bar equal to a sum over I of A sub I sigma bar I. Here, sigma bar I is an element of K for all I. And the A sub i's are real numbers. He says this is subject to the convention that if sigma bar I and sigma bar j represent oppositely oriented simplices, then we write sigma bar I is equal to minus sigma bar j. So for example, if we were to take the first two vertices and flip them, keep everything else the same, that would be minus this is the way orientation works. If you take any two vertices and flip them, that induces a minus in this wild world of M chains. All right. The vector space of all M chains on K is denoted CMK. All right? Now, it's about to get interesting. here we go. Let, yet another definition. Let sigma bar equal to P0, P1. This time I'll go to n, since he does. Be a oriented n simplex. All right. Of course, this could belong to some simplicial complex, but it doesn't really matter, particularly where it is belonging to. Wherever it belongs to, we define the boundary of sigma. But let's, for the sake of specificity, the boundary of sigma bar is an n minus 1 simplex oh, actually, no, not simplex. I gotta be careful. It's not a simplex. It's an n minus 1. It is oriented, but, well, yeah, I guess it's oriented. But I was going to say chain. And the definition here is quite beautiful. Here it is. Boundary of sigma bar is equal to the alternating sum. The sum, j equals 0 to n, minus 1 to the power j of this list with the jth one deleted. All right, so in other words, it's a sum, it's an alternating sum of n minus 1 oriented simplices, where we're doing plus minus depending on which one we're removing from the list. So here the caret means that the vertex p sub j is deleted. And, so extending linearly, to all of Cnk, we have the boundary map is going from what? It's going from n simplices, or rather n chains, I should say. It's going from n chains to n minus 1 chains, right, of a given simplicial complex. Because if you look at what it's doing, what's it doing? It's giving an alternating sum of n minus 1 faces of each thing in the chain that well, this, I've given the formula for just a single simplex. But more generally speaking, you'd have a sum of n simplex, and you'd take the boundary of each term in the sum. Each one of those terms is a simplex in K, which its faces, right, must all also be in K. So everything that's going on here is, again, built from a linear combination of things that are, again, in the simplicial complex by construction. So this is a well-defined mapping. It's linear because, well, we've defined it on a basis, actually. So you say, what do you mean? Well, that's the thing. The vector space in which we're working is taking the different faces as like a formal basis. Right? So it's not a vector space you've worked with before. Once we get into the example, this will become more clear. But yeah. Well, we could change these n's to m's. I actually would like to do that because I wanted to think about n as the universe in which this is living. The simplicial complex has some maximum dimension. If there's no simplex beyond a certain size, then we just say that C m of that k is 0. Are we talking about Rn or are we talking about m here? In which definition? The m chain definition. Good question. These have to be m simplices. Very good question, King. Yes, thank you. Good point. It's kind of important to not have said. My bad. Okay, so now let's look at some examples.
When they say that the EJ has hat on it, is it deleted?
Yeah, let's actually look at an example here. So let's let K be essentially, I'm just going to draw it sort of schematically. It's like the filled-in triangle, right? And then this one, and this one, and this one, and then, of course, this, and this. Sorry, I'm an idiot. So what I'm saying is, sorry, I'll stop. The two simplex, P0, P1, P2, right? This one, so if I'm saying this is P0, this is P1, this is P2, that one, then this would be what? With my silly picture, P0, P2, P0, P1, yeah, well, I gotta be careful. Yeah, I guess they should be ordered. I'm going this direction. What did I do? I don't know what I'm doing. Yeah. Well, I'm not. Do I have to? I'm not sure I have to consistently orient the subfaces for the simplicial complex. I mean, I don't want to insist on that. If you don't mind, let me just continue on here. There's something I don't. I will get back to what you guys want me to talk about in just a second. I know what you're itching to see. So give me a second here. I'll get this done with. Debatable plus or minus, right? What I should be putting in here, especially. I mean, there's obviously some choices there that could be made. But that simplicial complex describes a triangle which includes its interior, right? So here's the thing. If we look at the triangle, so now you guys tell me where to put P0. Anywhere? Okay, I'll put it here. Which one's where's P1 going to go? The top? All right. And then over here, P2. All right? So if we look at the boundary of P0, P1, P2, what you're going to find is that this definition reproduces the standard orientation for the boundary that we talk about in Calculus 3. Right? If I go Like, so you're, well, I don't know. I mean, I'm actually not sure if that's the case or not. I'm not sure that we've actually oriented this to have sort of the counterclockwise or the clockwise sense of the orientation. P0, P1, P1, P2, right? P2, P0. That's what I see there. That's actually the this is the clockwise orientation of that triangle. That actually would not be the standard orientation that we typically would give a subset of the plane if we were going to do Green's theorem and stuff, right? But anyway, just to illustrate the definition, that's fine. So the way this works, I delete the 0th one. I put -1 to the 0, which is 1. So that leaves me P1, comma P2, right? And then I do minus P0, P2, right? And then plus P0, P1, right? And then then flippity floppity, right? So this is what? P1, P2 plus P2, P0 plus P0, P1. Let me engage in some color coding here. P1, P2. See? P2, P0. P0, P1. I just think to me, that's so cool. But it's so much more than that. I gotta leave the lower definition. I really should have not written that in giant 30-size font. Oh well, too late. What if, let's see here, let's think about the tetrahedron. So let me just think about how I want to give it. What's the standard orientation of a three-dimensional solid? It should be like outward orientation, right? Which means that the right-hand rule, if you want to like imagine visualizing it, if I take a face, right, and I think about the right-hand rule, my thumb should point in the direction of the normal. So it should be like that, yeah? So if it's like that, let me just start with P0 up top, and then P1, and then P2. And then, let's see here. So that gets me started. I'm going to think of the tetrahedron as the 3-simplex, P0, P1, P2. And, well, I guess by process of elimination, that must be P3, right? I don't really have much choice in the matter, do I? But you notice my choice of labeling P0, P1, P2 was motivated by the right-hand rule, okay? Once I do that, what's the boundary of this? Right? But let's get rid of those minuses, yeah? I probably did it wrong. Let's see here. Oh, yeah, thank you. Let's see here. So what do you guys want me to flip? You can flip any two. Right. And I'll flip the first two. That's probably a definition that I should have made. I'm just saying you can flip vertices and it introduces a minus. I mean, okay. Probably to do that justice formally is another who knows how much, but let's.
I thought you're supposed to flip it the other way around, like only the first and the last one, not like two of them next to each other. Because I'm just imagining drawing a triangle. You go away here, and then you flip it the other way around, you cannot draw the triangle.
I don't think it matters. Let's see. I don't think it matters. But let's find out if it makes sense geometrically. 1, 2, 3. What's that? That's the one. Let me do it down here. So it's like down here. So 1, 2, 3, and so if you think about that, 1, 1 goes to 2 goes to 3. Oh man! What the what? Dang it! I want it to be outward oriented. One, two. No. Oh man. This worked last time I did it. What have I done? Yeah? They're all pointing inside? Oh, these are all pointing inside? Oh, so you're saying is my mistake was okay, so what you're saying is I'm just wrong in my construction. The calculation, good. So your point is the mistake is mine in thinking that I had positively oriented it. I've in fact negatively oriented, as is evidenced by the fact that going 1, 2, 3 like that makes it sort of, that's inward pointing, yeah? Right hand rule, if you kind of just the usual thing. And then this one, curses. 0, 3, 2, 0, 3, 2, 0, 3, 2. Oh yeah, that's also inward pointing, right? That one's also inward pointing. And if you look at, oh, that's funny. So I just chose poorly. Curses. 0, 1, 3. 0, that's on the back, right? 0, 1, 3. 0, 1, 3. Yeah, it's pointing in from the back. It's hard to see. I know at least do so much on the board, but yes, if we in fact examine these, we'll find out that I have in fact oriented the tetrahedron in the negative sense, as we typically talk about orientations of solids in Calculus 3. Remember, positive orientation is outward.
So is it not a problem that the orientation of the different line segments is different?
What do you mean?
Like in the P1, P2, P3, the orientation is going from 3 to 1, whereas...
Whoa. Wait a minute. What are you saying? I mean, didn't I do that here?
Well, there all of the orientation lines up with the... I'm more so saying, it doesn't apply to that. But for this one, with the first P1, P2, P3, we are saying that the orientation between 3 and 1 is going from 3 to 1. And the purple diagram is this through.
Yeah.
For the one that's P0, P1,
Oh, no, no, no. It's P0, 0 to 1 to 3,
Right.
and then back to 0 again. That's
1 is going to 3 there, and the first 1 degree is going to 1.
so. These are different.
That's what I'm saying.
Those
I'm
they're
wondering-
different faces. I mean, the vertex P3 is in the purple face. It's also in the green face, but it.
Right. That's what I'm asking. They can differ orientation depending on what face is talking about.
Well, I don't know. I don't think a vertex in and of its lonesome has an orientation. I mean, the orientation is something that is possessed by.
Well, yeah, not the vertex, but the segment between the 2 points. And differ depending on which face I'm talking about.
Yes.
Because I thought that when we did this construction, we were going to end up with an orientation of all of the faces that didn't contradict.
I don't think it does, though.
Right, that's what it doesn't, and so I'm asking if that's supposed to be the case.
Yeah. Yeah. I mean, I think that the. Ah. Yeah. Next theorem. Boundary squared, 0. So if you calculate the boundary of the boundary for either of my examples, let's do it. So here it's boundary squared of P0, P1, P2 would be what? So this would be P2 minus P1 plus P0 minus P2. I mean, yeah, P0 minus P2 plus P1 minus P0. And as you can see, a 0. And my example up here, let me make myself a little room for it. Calculate the boundary of this boundary. What happens? So the boundary of that would be what? P2, P3 minus, oh, I'm going to regret doing this. P1, P3 plus P2, P3, all of that from the purple. All right, well, hope you're patient with me. P3, P2 minus P 0 P2 plus P3 P2, all from the red. And then the green, we've got ourselves a P1 P3 minus P0 P3 plus P0 P1 all right, and then the last one, P0 P2 minus P1 P2 plus P1 P0. And if you get far enough away from the board, you should be able to see how those all cancel out. Right? Seems like a job for the pink marker. 2, 3 cancels with 3, 2. This 1, 3 cancels with that 1, 3. This 2, 3 cancels with this 3, 2. This 0, 2 cancels with this 0 too, because I had a minus in front of that one and a plus in front of this one. This one, 0, 3. Means I made a mistake somewhere.
Oh, you should have a 0, 3 from the red term, but it's not there.
Red term.
You write V2 twice.
Yeah,
Right.
you have
Oh,
V2 last.
this last. So
That one is,
P0, P3 there.
this one right here.
Yeah.
that one's V0.
So that one will cancel with this one. But what else did I cancel that with before? What? A 2.
Oh yeah, that the last one for the purple should be P1, P2, not P2.
Oh, good grief. All right, well that'll be important for when I get to the end of the list here. So, I mean, I've got at least like a B on this calculation, right? I mean, like about 80% right, or something like that. I mean, sadness. All right, that 1, 2 cancels with this 1, 2. And then this 0, 1 is canceled. So anyway, 0. In the handout that I posted, he has a proof that partial squared is 0 on an arbitrary, an arbitrary oriented simplex. And it's, yeah.
So this ends up showing that with the orientation that we gave to the faces from the original boundary, this shows that if we look at the orientation of the specific like line segments,
Mm-hmm.
that we always have to have a line segment going one direction and also going the opposite direction in a different face.
That's right.
Okay. Yeah.
Right. Yeah, as you may recall from like proofs of Green's theorem and stuff like that, when we break up the face into subfaces and you get cancellations along inner boundaries and stuff like that. Yeah. Okay, so the boundary squared is 0. Yeah. And all right, so let me get on with it here. So he says, now I finally have come to the point where I can tell you what a triangulation is of a space. What's a triangulation of a space? So here's the definition. A space X is triangulable if there exists a simplicial complex K whose set of points is homeomorphic to X. So, homeomorphism, of course, allows continuous transformations, right? So, like, example, a circle is triangulable. Because what we can do is we can envision the map that goes from the triangle. Not the shaded in triangle, but just the edges of the triangle, okay? This one chain. That is a triangulation of the circle. The homeomorphism from that triangle to the circle is just kind of like, if you can imagine this being a balloon, it's kind of go blow into it and it kind of just, whoop. That's a continuous map. In fact, the homeomorphism. The sphere, I mean, there are, you could have more complicated spaces where basically you can just form a bunch of triangles, like, a bunch of triangles that fit together and just fill out the space. That's a triangulation. And he mentions that many, many spaces are, in fact, triangulable. There are examples of spaces which don't permit a triangulation, but they're somewhat exotic, although there are famous ones. So if I was so foolish as to attempt to picture, now, here's another example. The disk, right? The disk would be triangulated by not just the triangle, but the solid triangle, right? In other words, you could use essentially, let's see here, P0, P1, P2. Those vertices and the edges, the one simplices which connect them, right, that would form the non-trivial simplices which triangulate the circle. This one, you would have, the same vertices, right? But this time, the simplices would be, there'd be more, right? You'd also have the two simplex in that one, right? Let me be more specific here. The zero chains, in this case, would basically be what? Include P0, P1, P2. Zero chains in this example. Again, the vertices, P0, P1, P2. One chains. You got yourself, P0, P1. You got yourself a P1, P2. You got yourself a, what's the other one? P0, P2. Okay, I'm not worrying about the orientation or anything like that. Those are the independent. You're like, well, you've also got P2, P0. That's true, but that wouldn't be independent. So in the style of the calculations here, it's reasonable to think of those as independent. I can't get one of them from the other through a linear combination in the calculations that we're doing. C1 is also the same here in terms of what the one chains that are, the one simplices that are allowed. One chains are what? They are linear combinations of these guys. Yeah? Over here is where it gets interesting. C2, 0. There is no two simplex in the triangulation of a circle. Over here, C2 has got something. C2 has the P0, P1, P2. Right? Let me summarize. For both of these, C0 is, let's say, three-dimensional. For both of these, C0 is three-dimensional. For both of these, C1 is three-dimensional. For the disk, C2, when we look at the set of all chains as a vector space, it's one-dimensional. It's spanned by that one two-simplex, P0, P1, P2. For the first example, though, C2 is just zero-dimensional. So these are vector spaces. There's a vector space of M chains that we can build corresponding to the different M simplices which exist at each order for the object we're looking at. All right? But we also know that we have this boundary map that goes from M to M-1 chains, right? And this is what allows us to set up what's called homology. So I need to define something. So here's the definition. So this is what I'm describing right now is simplicial homology, which is homology built from simplices, all right? So in particular, an M chain C bar with boundary of C bar equals to 0 is called a what? M cycle. We say Z MK is all M cycles in M cycles over K, let's say. All right? So that's an M cycle. There's also something called a M boundary. An M chain, let's say C bar, such that C bar is equal to the boundary of C bar prime for some M+1 chain. C bar prime is called an M boundary. And the set of all M boundaries is denoted what? BMK. All right. So here's the definition of homologous. Two M chains are said to be homologous. I feel like I'm mispronouncing that. Oi. Let's say, C bar and B bar in CMK. So CMK, remember, is the set of all M chains built from the simplicial complex K, right? So two M chains, C bar and B bar, are homologous